Hello everyone. Imagine a massive glass skyscraper facade. Everything looks perfect, and then suddenly, without a warning, a glass panel spontaneously shatters into 1,000 pieces. No impact, no weather event, just boom. Alright, so today we are looking at the material science behind tempered soda lime silicate safety glass to understand exactly why this happens and how advanced factory engineering completely eliminates the problem. To understand the failure, we first have to understand the chemistry. Alright, so glass starts as an amorphous frame, a random, non-crystalline array. We use silicon dioxide as our network former to build strong, covalent 3D tetrahedra for chemical defense. We also add sodium oxide as a network modifier to lower processing temperatures and melt the viscosity. Finally, we log in calcium oxide as a stabilizer to cut down water vulnerability and restore environmental resilience. To give this glass its strength, we use advanced tempering mechanics. We heat the glass to a thermal soak state between 620 degrees Celsius and 680 degrees Celsius, well above its glass transition temperature. Then, we heat it with a symmetric convective quench, a rapid air blast on both surfaces. The surfaces freeze instantly into a rigid microstructural gauge, while the inner core cools much slower. As that inner core eventually contracts, it pulls on the outer shell, freezing a protective surface compressive zone exceeding 69 megapascals, which is perfectly balanced by internal tension. But if the engineering isn't perfect, catastrophe strikes. There are two primary failure modes. First, subcritical mechanical fragmentation. If the factory quench pressure is too low, it yields a shallow, fragile, compressive shield. A simple surface scratch can easily puncture right through this thin barrier into the high-tension core, prompting unprovoked total shattering. Second, and more notoriously, are chemical nickel sulfide inclusions. This happens when trace nickel from machinery combines with sulfur from furnace fuel. The rapid air quenching process accidentally traps these microscopic inclusions in their unstable, high-temperature alpha phase. Over months of ambient storage on site, this inclusion slowly tries to revert back to its stable beta phase. This solid state shift triggers a massive 4% volumetric strain. As the particle expands in the glass core, it creates intense, localized stress concentration points until the entire panel spontaneously bursts. Alright, so how do we solve a microscopic problem hidden inside a solid panel of glass? The definitive solution is mandatory factory heat soak testing, or we call it HST. We place all finished tempered sheets inside a quality control oven and uniformly hold them at 290 degrees Celsius plus minus 10 degrees Celsius for a minimum of 2 hours. This thermal treatment acts as an accelerator, forcing the sluggish, latent alpha to beta phase transformation to happen inside the factory. Defective panels fracture safely in the chamber rather than high up on a building facade. By combining this testing with optimized heating dwells, 650 to 670 degrees Celsius, and automated quench pressure calibration, we guarantee a robust surface compression layer. Through precise chemical control and rigorous thermal stress testing, we turn unpredictable glass into a completely reliable structural shield. So that's it from me. Thank you.